Yeah. All right, we are back to the second lecture, which is about hierarchical clustering. So what is hierarchical clustering? It's about bringing us further down from, let's say, a few hundred, a few thousands assets to a few assets. And so the question is how we want to do that, right? One way of going about that is that we know that correlation is something which will come in handy when we talk about asset allocation. We know from the Markowitz way of thinking that diversification comes. A well-diversified portfolio of assets is one where the assets in the portfolio are not highly correlated, right? So high correlation between assets means that if you buy one of them, it's just as good if you have 10, extremely positively correlated assets. If you could just buy one, or you can buy all of them. If they're all positively correlated, then what difference does it make? It doesn't introduce any diversification to your portfolio. So diversification comes, the idea of diversification is if one of the assets is doing badly, then there is some other asset which is not positively correlated to that. Then that one is maybe not doing as badly, or maybe even doing great when the other asset is doing badly. So in that way, they kind of compensate each other's bad effects at the bad times, right? So that's why we want to look into correlation when we're talking about assets. So now let's see if we can do something about that. Right, and we do that using a method, a machine learning method called hierarchical clustering. Hierarchical clustering is inspired from kind of our way of always wanting to, put things, objects, people, whatever we see and deal with into groups, right? So it's also kind of the engineering way of thinking of dividing and conquering, right? So if still you have the same problem, I give you 1,000 assets, and then I ask you, well, can you bring it down to 5, which is going to be your portfolio, and it's going to perform well in the long run, right? So that's kind of the problem you get to work with, right? So one way of going about that is saying, all right, I know that correlation is useful in the sense that I want to find some assets which are not highly correlated. Let's say you want to find some assets which are under uncorrelated, as uncorrelated as possible, and then you want to group them as such. So I give you 1,000 assets, group them in, let's say, 10 different groups, and these 10 groups have to be as little correlated with each other as possible, right? This is something that if it was, if I will tell you, well, in this class, who are the girls and who are the boys, then you can make easily 2 groups, right? So that we can do. But if I tell you, well, these assets, I have 1,000 assets, put them into 10 groups that they are as uncorrelated as possible with each other across the groups, and in each of the groups, they are as correlated as possible. So that is the task that we have a method called hierarchical clustering for. That's, by the way, called unsupervised classification, because you're just learning from the structures of the data themselves. You're not putting any kind of model on top of the data. You're just using the underlying data itself. It's called unsupervised classification, or unsupervised learning also it's referred to as. Right, so it's best shown with an example how you do clustering. So I'll show you first how this is done in a plane, in a plane like this, where the distance between 2 points, as you know, is the Euclidean distance, is the measure of how you find out how far apart two different points are in a plane, right? So this is simple, and then we're gonna see how does that work when you're looking into assets, and we want to measure the distance between these different assets, the ETFs, based on their correlation characteristics. All right, but let's start with the example just to get an idea of what hierarchical clustering is. So I have these points. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 points, and I want to put them let's say, well, I mean, in as many groups as possible in such a way that the groups are as far apart from each other as possible, right? So one question could be, and you could probably just say it with that, if the question to you was put it into two groups which are as far apart from each other, how would you group them? So, right, so I can see already all the ones there on the right. This is one group and this is one other group, right? So you can just make two, and that's kind of done, right? So our brain kind of works quite well in things which work in 2-3 dimensions. We can figure that out. We can, if we have an understanding, natural understanding of the distance that our brain kind of understands, our eyes capture it, then we can do it immediately, right? So this is quite easy. So let's start with that and say, well, how we can do this in a systematic way. So how is this done? So this was what you just did. So this is the 2. And then you can do further into 3 and so on, right? Now, so that was kind of the visual way of doing this. Now let's do this using what is called agglomerative hierarchical clustering, which is essentially an algorithm which is doing more or less what your brain simply did. Now we want to put it into an algorithm. So what is the idea here? Here is that we have to introduce something called a distance measure, dij, which measures the distance between 2 points I and j. In our case, is just the Euclidean distance between 2 points, right? And then what we do is that we compute what is called a proximity matrix using that distance. The proximity matrix is that we want to know what is the distance from each one of the points to all of the other points, right? So that's the first thing you would do. I mean, you didn't quite do that. Your brain works faster than that, right? Because you can just see it. You don't really have to do the calculations. But if you want to do it in a computer, there is no other way. It has to go the slow way. You have to first measure the distance from each point to all the other points, right? You do that, right? So that's your proximity matrix. Then you say as far as the number of clusters is greater than 1, and this is the case, right? We started with 11. So we just say that we have 11 points. Let's say in the one extreme, the 11 points are actually each of them their own cluster, right? So you start with 11 clusters in one extreme. In the other end, you have one cluster, which is all the 11 points, right? So you have the two extremes. So the agglomerative clustering starts from the individual, and you have number of, you start with the 11 clusters, and you go down to 1. So as far as the number of clusters is greater than 1, then you merge the two closest clusters. So I take 2 points which are closest, merge them together. Then I update my proximity matrix that reflect the proximity between the new clusters and the original clusters, and then you continue, right? So what does that mean in practice? So I start with the 11 points. I'll make them into clusters, right? And then now I have, each cluster is made up of 1 point. I measure the distance from all the points to all the points. I have my proximity matrix. And then I'll merge the two which are closest to each other. Well, that happens to be these two. Now I have 10 clusters. I had 11 a second ago. Now I have 10 clusters. Now the question is, how I have to remeasure the proximity matrix. Now this guy is a new cluster. Notice even though, just before I had points, but I call them clusters, represented by 1 point. Now I have one cluster represented by 2 points. Now I have a new problem. How do I measure the distance between this cluster and any other clusters around it? I can do it in a number of different ways. It could be, for example, that I decide, well, I want to get the point which is closest from in this cluster to the point which is closest to that from the neighboring cluster, right? So that I have to then make kind of some assumptions for how I measure the distance between one cluster to the other. I have to have a representative for each cluster, right? So if my way of choosing a representative from these two clusters was, for example, picking up the ones which were closest to each other, then well, that method is called the linkage method. It's called single, and then we have a few more that I'll introduce to you in a bit. But for now, let's say I'll just measure the distance between this cluster and all the others, And then I'll find out these two guys were then the ones which were closest points, so they come into a cluster of their own. And then these two guys. And then here now we have 3. So right now I have 1, 2, 3, 4, 5. Next point, and here we go. Now we are back to kind of our 2 clusters, and finally we have the whole thing. So essentially it just starts simply by measuring the distance between all the clusters to each other, putting the 2 closest, merge them together, repeat, and go on until you have one total cluster. And what you get in the process is this. So then you can cut, what you get is the so-called dendrogram. So what we started out with were these 11 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then we get these 2 guys together at one level. So now at this level, we don't have 11 points, but we have 10, right? And then at this level, we get these 2 guys together, and then you get these 2 guys together, and so on. So at some point, if let's say, if I'm cutting this dendrogram at this level, then that tells me there's 1, 2, 3, 4. So there are 2 representations of this, right? I have 1 cluster, 2, 3, which is made up of only 1. This one is this guy, right? And then I have 1 here, which has got 1, 2, 3, and 4, right? Most likely, yeah, well, this guy, right? So that's how you can read the results of your clustering. So this is when you're talking about pairs. Let's go into the linkage method. So how do we measure distance between a cluster and the neighboring cluster? It could be done, for example, using the so-called single linkage. That was the closest 2 points. Or it could be done using the complete linkage, which is the 2 ones which are furthest apart. It could also be used, there are a couple others which kind of get some sort of average representative for the cluster. Right? Okay, I'll just show you an example of how this one and a study like this could be done. So in asset allocation, well, how do we do this when it comes to asset allocation? So far we've been talking about points, right? And we were talking about points. Then the distance between 2 points was just the Euclidean distance, right? But when we're talking about ETFs, right? How do we, and we are interested in measuring the distance between 2 ETFs. We can't use the Euclidean distance, right? Because, well, what are the coordinates of the ETF, right? But what we can measure is the correlation, or the covariance between 2, right? Covariance then turned into correlation. What is the range of a correlation? It goes from 0 to 1? Yeah, minus 1 to minus, sorry, minus 1 to plus 1, right? So correlation goes from minus 1 to plus 1. Correlation is kind of the normalized covariance, right, between 2 assets. So could it be an idea that when I say, let's say this is the correlation C of assets I and J, right? This is my correlation. And this one belongs to the interval minus 1 and plus 1, right? This is how the correlation works. Now, what I'm interested in is the distance between I and J. So if I say the distance between I and J, could it be, for example, what happens if I say this distance was, let's say, 1 minus Cij? Right? Then Dij, which is the distance between these 2. So if I have 1 minus 1, that would be 2, right? And if I have 1 minus 1, 0. So in that way, I'm transforming correlation between 2 assets depending on my understanding of what I really want to achieve. So let's say what I wanted to achieve was to say, well, the two assets which have got the highest negative correlation, I want to consider them to be as far apart from each other as possible. Then this one is a reasonable measure of distance, right? Because this one tells me I'm in my distance space, the distance goes from 2 to 0. 0 means these two assets are identical, meaning they have a correlation of 1. And 2, that's as big a distance as I possibly can get. And that's the case where these two are kind of the diametrical opposites of each other, right? If the one goes 100% up, the other goes, if the one goes up, the other one goes 100% in the other direction, right? Going up by of assets which do that. I mean, well, you can construct that, and that's actually you can always have a long and a short in the same asset. Then they will be 100% negatively correlated, right? But if it's not constructed, so if you don't have a long and a short position in the same underlying asset, right, then you can still have some assets which are negatively correlated. Normally, bonds and stocks are known to be negatively correlated. In times of crisis, then they might get positively correlated still. But in average, they are considered to be negatively correlated, but not as much negatively as this one. So you don't get kind of negative correlations close to -1 are very rare. You would hardly get that. But then you can find assets where the correlation is around 0. That means they are uncorrelated. And also, there's always this discussion: what's going to work better? Are you in favor of negative correlation, or you are in favor of no correlation, right? Because if you are in favor of no correlation, or let's start this the other way. Let's say if you are just purely in favor of, well, let's say, well, I buy this. This is a good distance metric for stock, for assets, for financial returns to financial assets in terms of their correlation. I want to go with that, right? Then I'll say the counterexample. I'll make a short and a long position in the same underlying, right? Then I'll get a beautiful correlation of -1 per construction, right? Short position, long position in S&P 500. Do I want that? Do you want a portfolio which wants to find assets which have a correlation? I mean, -1 in Markovich, the same idea, right? Markovich really likes this negative correlations. So the more negatively correlated two assets are, the more likely they are that they are put into a portfolio in order to minimize risk, right? But the counterexample to that, what happens if I had a short and a long position on the same underlying, let's say S&P 500? What would Markovich do with that when it's minimizing risk? Let's say it can only go, it can buy, I mean, you have, and these products, by the way, are found. Let's say I say a short S&P 500 and a long S&P 500. And by the way, you can buy ETFs on that. So you can have an ETF which is 100% long in S&P 500. You can buy another ETF which is 100% short in S&P 500. So if I had those two ETFs, what would Markovich do with that? And I want to minimize risk.
If they buy both equally or none of them, doesn't matter.
Right. Because, well, I mean, if I have to buy.
If I have to buy equally.
Yeah, if I have to buy 100%, then it goes 50% in this and 50% in that. Because it gives
It cancels it out.
It cancels out, so it gives a risk in terms of variance of 0, right? It gives a variance of 0, and that the variance of 0 is what is important in Markovich, right? But from a asset allocation point of view, would that be an interesting portfolio? No. Because what else is 0? Returns, right? But and minus the costs, right? So if you have these kinds of costs on top of it, or even these kinds of costs, 1 to 3%, or even 0.1, whatever costs which you have, then you will get 0%, and you have to deduct the cost. So you're sure you get, essentially, you're going to lose money with 100% certainty, right? So that's kind of one of the counter examples for why you don't want to necessarily go after negative correlations. In some cases it makes sense, but in the cases where you have, I mean, definitely you have to check up that you, in your portfolio of ETFs, you don't have both short and long of the same underlying, and then you put it into Markovitch. Then it's, it's a recipe for disaster. Then your model will do all kinds of stupid things, right? So you want to check for those things. That's part of the feature selection process, right? But what else we can do? So I can also say, well, this is one alternative. I can also, let's call this d prime, ij, and I can say it's equal 1 minus, and then I can have the absolute value of this, right? So what happens then? Then my, sorry, that was my distance. So my distance here becomes, so that's 1 minus, 1 minus 1 is 0. So it goes from this, so the distance in this end is 0. And 1 minus 1 distance in this end is also 0. But what happens in the middle? Because there's also something, it goes from minus 1 to 1. So there is also a 0 in between, right? 0 means no correlation at all. So 1 minus 0 is 1, right? So then this guy goes from 0 to 1. Now I made another. So this one went from, probably it's better to maybe actually even to be quite exact. So I have to say it goes from 0 to 2, right? So this distance metric goes from 0 to 2. This one goes from 0 to 1, but the interpretation is that 2 here was for the case where they were 100% negatively correlated. 1 somewhere in the middle was for the case where they were non-correlated, right? So that was 1 minus 0, right? Would be 1, sorry. So it goes from 0 to 2. Here it only goes from 0 to 1. So the two ends are 0, and the case where the two assets are uncorrelated, where the correlation is 0, has the largest distance. So that would be another interpretation. So these are the kind of things that you want to play with when you do an asset allocation, sorry, a clustering on assets. Right. So let me. Okay, so this is probably a good example I wanted to show to you here. So this is one hierarchical clustering that we did with 96 ETFs. And what we wanted to achieve was how to come down from 96 ETFs to 10 ETFs. And here's the result. You get this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what you do with that is that you use Pearson correlation to get the correlation matrix between the 96 ETFs, right? And then you will measure, and I'm actually not quite sure here which one of the two metrics are used, if it's this one or that one. You can use either of the two and see what the final result is going to look like. And then you will do a hierarchical clustering. You get your dendrogram, and you cut it at the point where there are 10 clusters, right? And then you will see which clusters are in there. And then in this particular case, then you have to pick up one representative from each cluster as well. So you get 10 different clusters. And in this case, we are picking one with the lowest standard deviation. You could also pick maybe one with the highest Sharpe ratio, or the one which is the most representative of the group, or has got the most return, or something else that you favor. And then this is a kind of a final test that you can do. So notice here, just to make sure whether or not our clustering here worked. We did the clustering using correlation and that distance measure. And then we are looking into these 10 assets and look what the return of these guys have been, the 1-year return of these have been in the period for which we have been doing the clustering. Right? And you see that there's some of them, they have very good returns. And some of them, like the first one, has got, the MSCI Malaysia has got a very, very negative return. So is this a sign, just a question for you, is this a sign that the clustering has been working? Or is this a sign that the clustering is garbage? I mean, because who wants to go with the negative? We are doing feature selection, right? But why would you want to pick up some assets which have negative returns? Still, this is what and then you want to bring this into your optimization. Yeah.
To reduce risk and diversify?
Right. So it's just and can somebody elaborate more on that? How that's done? So how does that reduce risk if I go with if I'm picking a number of assets which for last year actually they were giving a negative return?
If another asset would give or would be which is now positive or which gives now a good return, which would into negative return, the other ones would go into
Right.
direction and they would.
That's the whole idea of that they are either uncorrelated or negatively correlated, right? So the point is that, well, you know, the assets which have been doing poorly last year would not necessarily do poorly next year. You have to. It's not. You can't look in return alone. You have to look into diversification among the assets and into the correlations if you want to reduce your risk. And so that is essentially a sign that the clustering is working. I'm going to wrap up by showing you. Let's see if this one works. So we want to now wrap up with choosing 10, 15 assets together that we can use for the final project. So we built, you know, after that project was over, build a little demo which actually does this clustering in a package called Shiny in R. So that's R, which is underlying this. So let's see what's happening here. If you wonder if you can see, I have 1,928 assets here on the top, and then I want to bring them down to, you know, like maybe 10, 15 assets. So let's do this together. Let's go and do some screening first. So what I want to do is that I want to pick up from all asset classes, equities, commodities, fixed income, alternatives, asset allocation classes, and currency. So these are classes and from all different regions. I don't want to have any leveraged ETFs, and I don't want to have any short ETFs. So I only have long positions, and they are non-leveraged, right? And that brings me down to 1,085. So now I'm doing kind of my first simple screening. Then I want to go further down and say, well, at least I want 10 years of data. So I don't want to look into something which has got less than 10 years of data. Maybe even go a further point and say, well, I want 12 years of data. Because now I think this data ends in 2017, so 12 or even 13. Let's see how many is left. So if I want 13 years of data, then I'm only down to 180, right? Then maybe I'll go back to 12.
Many of them won't have
291, sorry?
Many of them won't have data, but the underlying data still exists, right?
Well, the underlying, yes, but then that would be too much of a hassle for a course like this, yeah. But so these are, you know, so I'm looking into ETFs only, so the ETFs which have been around for, in this case, 12 years, right? So let's keep to this 291, and this is, so rather than, you know, now we are doing a hierarchical clustering study live using this. So I'm going to go further with 291. I want to do a clustering on that. So this is a clustering machine, and let's say, oh, I don't want to do 10, but let's start with, I might want to do 5, and then I want to pick a few different, based on a few different criteria, right? So I'm using, you know, Spearman correlation coefficient, by the way. I want you to check up what is the difference between Spearman and Pearson. But let's just, for now, just say that I'll prefer to use a Spearman. You can think why. Then here we've got these two methods. So it's, as a standard, I use 1 minus the absolute value of correlation. So I'm interested in getting uncorrelated and not negatively correlated clusters. Then there were these different linkage methods, just to give you a sense of how this works. So if I go for the single, which was kind of the most simplistic way of measuring distance between two clusters, and then I'll perform my clustering. So now the clustering is done. And if I go to the next page, where I can see the results of this, so it just, look, these are the clusters. So actually what happens here, I get a picture of that many of these assets are in one cluster, and then the other 4, they are very small clusters each. So this is not a very good clustering. This is just based on a bad method of linking the two clusters together. So if I go with the complete, which was looking at the 2 points which were furthest apart into 2 clusters, and then I repeat my clustering, I'm doing everything exactly the same apart from the way I'm measuring the distance between two clusters. And then what happens? It gives a much better diversified way of clustering. So clustering is kind of an approximative way of looking into things, obviously based on your assumptions. That's why you have to be very critical of the underlying models you use. So if I only accepted the single linkage as the way to go ahead, then I'll get kind of not very interesting clusters to go ahead with and do my asset allocation. So that's where, and this gives actually some probably more interesting assets in here. But let's say if I can do even better than that. So if I go back and I prefer this word D, which is kind of trying to find out what is the optimal way of finding out the points which give the most total diversification across all the clusters. So somebody actually went into effort of figuring that out and making an algorithm for that, just to measure the distance in a more advanced way. And then you can see the result of that is, well, this is probably maybe difficult from this one to see, but this is slightly better than the other one. So I'm going to go on with that and choose this one, which gives me the most diversified clustering algorithm, right? And what have we got here? So what I've done, if you notice back here, I'm picking up the ones which are the most representative of each cluster. So if I go back again to the results, what does it mean? Here I'm showing these 5 clusters, and the red points are the ones which are the most representative of them. So these are the 5 assets which are as uncorrelated with each other as possible among these 291. This is essentially what we're doing here. So that might be a good way of going about this. Well, this one actually in cluster 3, that guy seems to be the one which is also performing the best in terms of Sharpe ratio. So SR here means Sharpe ratio. So has got the best Sharpe ratio for the period we were looking at, right? So let's get a stock. Let's pick those 5 then. So we want to write these names down, and we want to then, I want you to study what they are, and I'm going to find the data for you. So what have we got? This is D. These are the tickers, by the way. DWM, which is an equity class from developed markets. These are all, by the way, denominated in US dollars, these ETFs. Then you have RYU. You have TIP. TIP is an interesting one. TIP is a fixed income. Stands for Treasury Inflation Protected. So in the US, if you want to invest, put your money into an ETF, which more or less gives you the same return as inflation. Essentially, the ones to keep the value of your money in terms of its buying power, then you can buy some TIPS, right? So that's TIP. Then there is one called VTI, and VTI is North American market, and then XLE. So those would be interesting to look at. Now, it might be also interesting to look into those with the lowest Sharpe ratio, the lowest standard deviation, minimum historical standard deviation. So I do another clustering there. It's the same clustering, I'm only picking a different asset from each cluster, right? So if I go back to my clustering results, now I just get 5 different assets. These are kind of the low-risk assets. So notice what happens here. So these are the next 4 assets I'm picking up. That's one called DBV, which is an alternative asset for developed markets. And then FXB, which is currency, Europe. It's in pound sterling. You have RYU. North American equity. Then you have SHY, fixed income North Americans. And then you have Treasury, American Treasury. And then VDC is also, VDC is actually a very interesting one as well. It's consumer non-cyclics. So consumer is you know, it's an index of all the consumer goods, right? So these are the things that we have to buy and eat. You know, there's the edibles, you know, the things you buy in the supermarket. So that's everything in that category is put already into an ETF called VDC, consumer goods, right? So far we have 10, and shall we pick up some more? Maybe what we do is now just to see what else would I get. So if I go back here and say I want to get some more, sorry, I go back to a clustering and say I want to get not 5, but let's say I want to get 3 clusters, and the ones with the I want to pick the ones with the highest Sharpe ratio. Last one. And let's see if there is any overlap. All right, then I pick up 3, and now actually there is no overlap. There is a fixed income called AGG, which is also a good one. And then you have the DLS, which is an equity, small cap. And then you have the RHS. Right? No overlaps as far as I see. Scott, it brings us to 13. Sorry? Which one? RYU and RYU. All right, so that one is a repetition. So minus that, so that's 12. I think that's still fine. 12 assets, and they are kind of, well, what we know for sure that they are not very correlated, right? So that's kind of my conjecture here based on what we went through here. We applied hierarchical clustering using R, and showing that I can, in a couple of minutes, I can find you a handful of assets from a few thousand assets, in this case ETFs, which are as uncorrelated as possible. You know, and then I'm picking them up based on some different characteristics. Some of them based on being more representative of the group, some of them based on being very little risk, and some of them based on being like high performance. Right? That's a good way of mixing, a good mix of assets. And then the next question would be to, we have to do bootstrapping of generating some scenarios on these, and then run some different asset allocation strategies for that, and then doing in the sample and out of sample testing, which was the topic of last lecture, right? And any questions to this so far? Anything about either ETFs or about clustering? It's all clear? Yeah, there's one there.
Can get ETFs.
Sorry?
Where can buy ETFs?
Where can you buy ETFs? Well, I mean, you can buy ETFs on essentially on any investment platform, any exchange. They have it in Denmark. It's probably the easiest way of going about it is to go on an online platform like Saxo Bank or Nordnet. There are a couple of international ones. You have Interactive Brokers. You have eToro. These are very simple online investment banks which allow you to trade all kinds of ETFs. Some of them have more options than others. Nordnet has more like the European-based ETFs, but some of the other platforms are just international. All right, so let's take the next break, and then the rest of the time goes to working at some point before we leave, half an hour. I'll go through the how you do the bootstrapping, not based on these because we don't have the data for that yet, but based on the data that you have on the example of last week. All right.